ladies and gentlemen, and my name is Jiayin Chen, and from the Southwest Jiaotong University in China. Today, I'm going to share some recent advances in the field of the turnout damage analysis. The topic is the numerical investigation of wheel turnout rate dynamic interaction and the contact damage mechanism with wheel profile evolution. Okay, I will first discuss it from the background and the problems about the performance evolution of the turnout and the wheel. Then I will touch on the methodology about the vertical turnout coupled model and the analysis method of the wear and the rolling contact factor. Then a case study was put forward considering the wheel profile evolution. And finally, the future work will be discussed. As we know, the wheel rate relationship in turnout is more complicated than that in the interval line. The figures on the left side show the typical damage types in the Chinese high-speed railway turnout. And the figure in the upper left shows the longitudinal crack on the straight switch rate side. And it is caused by the incorrect grading method. And the figure in the lower left shows that the great deviation of the height frequencies between the stock rate and the switch rate. And it causes the abnormal light band within the transition scope in turnout. Meanwhile, the wheel profile evolution will affect the wheel rate relationship in turnout. And the holy wear is the most typical one. The figure in the lower right shows the measured wheel in Chinese high-speed railway vehicle. And it is found that when the operation mileage reaches 250,000 kilometers, and the holy wear exceeds 3 millimeters. In detail, when the holy wear are formed and the curvature at the holy bottom of the wheel is smaller than that on the rail head, so the contact position may shift laterally to the contact point B or C, but instead of point A. So considering the multi-port contact in turnout and the varied cross sections, the wheel rate relationship may get more complicated. Okay, as far as the methodology and the Simplex software is used to build the vehicle model. And in order to consider the precise contact fixation and creep age, the flexible wheel set is used. And after obtaining the free model of the wheel set based on the finite element platform, the flexible wheel set is employed in the vehicle model via the FEMBS interface. And because the wheel set is subject to the root constraint by the Asia balls and the primary suspension. So the A frequency of the vehicle and the flexible wheel set coupled model is obtained. And the 29th coupled model, whose frequencies is up to nearly 1,400 Hertz, are considered. Finally, the smooth cross sections of the turnout are obtained by the interpolations. And they are used as the inputs to the Mooney inertial turnout model. After obtaining the dynamic interaction in the turnout, we calculate the wear index. Then the surface initial rolling contact factor index is evaluated too, based on 3 assumptions, including the elastic, Hertz contact, and the fluid slip. For the first one, elastic, we use the contact software to do the rolling contact analysis in turnout area, and only considering the elastic materials characteristics. And for the second one, the Hertz contact, it is thought that the wheel rate contact in the center of the stripe meets the Hertz contact assumptions, and the RCF distribution is shown in this central figure. And for the last one, fluid slip, and another approach to simulate the partial slip condition is to relate the wear index with the RCF index by the Plancke function. And finally, we consider that the contact information is constant during the wheel rolling through the specified ray profile, and the accumulated RCF is evaluated. Now we will move on to the case study, and we consider the wheel profile evolution. As shown in this figure, and the simulations of vehicle passing through turnouts in the straight route of the facing booth in the speed of 350 kilometers per hour is carried out. And it is found that with the profile evolution, the maximum vertical wheel rate force decreases from 106 kilonewton to 78 kilonewton. And the position of the maximum vertical force is shift backward. As far as the lateral displacement of the wheel set, and this figure shows the simulation results. And the positive value means that the wheel set will move towards the straight switch rate side. And it is found that when the operation mileage is below 100,000 kilometers, and the maximum natural displacement of the wheel set increases in the switch panel, and the acceleration is accelerated. When the operation mileage reaches 150,000 kilometers, the amplitude is close to 0. But on the contrary, when the operation mileage is above 200,000 kilometers, the wheel set will move in the opposite direction laterally in the switch panel. We will discuss this later in a little more detail as we go on. Okay. And this figure shows the contact point trajectory on wheel at the straight switch rate side. And I divided these figures into 3 parts. Part 1, Part 2, and Part 3 means that the contact point position before the wheel transition, during the wheel transition, and after the wheel transition from the stock rate to the switch rate. And the rectangular means the holy wheel area, and the outside edge of this area means the frost flange. So we can find from these figures that for the part 1, that the contact points are located near the frost flange when the operation mileage is large. It causes the reverse movement of the wheel set. For part 2, it is observed that the wheel transition position is shift backward. This is the reason why the position is shift backward to the stronger cross-section of the turnout race. This is the reason why the vertical wheel rate force decreases. And for the part 3, the contact point mainly located on the edge of the holy wheel, and the multi-point contact area is enlarged. As I mentioned before, with the wheel profile evolution, the wheel transition position is shift backward, and that the natural contact irregularity is enlarged. So the natural spur index increases from the 1.73 to 2.51 by 45%. For the wear index, it is found that with wheel profile evolution, the maximum wear index in the operation mileage range from 50,000 kilometers to 150,000 kilometers is nearly 2 times larger than that of the wheel profile. Okay, we will discuss this figure now. This figure shows the distributions of the accumulated surface initial RCF damage in switch panel after one vehicle passage. And the figure A shows the simulation results of the new wheel profile. And it is found that the maximum RCF is mainly focused on the head and on the top of the ray. And so with wheel profile evolution, we focus on the figure B, C, and D. And the wider RCF bands are found not only on the top of the switch rate, but also at the gauge corner of the race. And basically, the point is that with wheel profile evolution, the maximum RCF value decreased by 91%. Meanwhile, the similar conclusions are found in the crossing panel too, So we can draw the conclusion that when the holy wheel are found on the wheel, the rolling contact factor damage may decrease. It is speculated that there are two reasons. First of all, the first is that the wheel profile evolution may improve the wheel rate conformal contact that enlarges the contact patch and decreases the contact stress. And another one is that the wheel transition positions are shift backward with wheel profile evolution, and that it decreases the wheel rate impact in the turnout area. In the future, we will consider three characteristics. The first one is the relative motion of the rays in turnout, which is one of the most outstanding characteristic in turnout. And another one is that the two-point rolling contact analysis, considering the conformal contact, will be improved. And finally, the simulation with the vehicle passing through turnouts in the divergent route will be carried out later. And if you have any problems, I will be very delighted to communicate with you. And thank you for the privilege of presenting my paper here. Thank you.
Thank you for your presentation.